Welcome back to the third part of chapter 6, latches and flip-flops and timers. So we are still discussing this type of circuits. Now the idea of counters was explained in the last video, and now we are taking another type of circuits that we haven't yet studied. Now, in brief, timers are actually circuits that count for you a certain, let's say, period, or they go on or high for a certain period, then they go off, back again on, then off, depending on the design. Based on that, we have two types of timer circuits or timing circuits. We have the one we refer to by one shot, and as the name indicates, it's a monostable, actually, multi-vibrator. That means it has its own triggering time, then back again to zero, then we trigger it to high, back again to zero. It's not exactly bouncing between two levels based on a certain period. Rather, it depends on an outside exciter, or it needs an excitement from outside. We have the other type, what we call free running, or the astable multi-vibrator. For the astable, it keeps bouncing. It's not stable, okay? It's unstable. It keeps on bouncing between two states based on a certain period. Okay, for the monostable, as I said, it has its own stable operational process. Usually we keep it in that stable operational process, then we trigger it to go to unstable process and then starts counting. Then back again to a stable process, trigger it again to unstable, and so on. Okay, so that is these are the two types that we have in timers, and we will see how we can design them using basic electronic circuits or chips. Okay. All right. Now again, we mentioned about triggering. It's very similar to clock. It depends on either a trigger like a rising edge or a falling edge. This is an edge triggered. Usually these cases are edge triggered. One more thing I have to explain. We explained about timing. So we said about the monostable. We trigger it, let's say the one shot. It goes from its stable state to unstable states and starts counting. Who counts? So we have a counting circuitry or a counting circuit. Usually any counting circuit in that case, or timing section, is composed of a resistor. So you guys must have learned the resistors in physics, resistor and the capacitor. These usually combine like a timing component or a timing section, okay? And once we trigger such a one shot or monostable, it goes to its unstable state and then begins counting, and in that counting is discharging or charging. It depends. In this case, it is charging through a resistor, and the counts goes like that until fully charged up to certain level, not necessarily 100%, but up to certain type. Then back again, we may trigger it, we go discharge, and so on. Okay, this is the idea in basic sense. I haven't yet stated any details. So look at the timing section. We have the logic circuit, we have a triggering, maybe rising edge, maybe falling edge, it doesn't matter. We will create a period. This period is determined by the instability or the unstable time. Okay, it may be high, it may be low, it doesn't matter much actually which one is high, which one is low, because we can invert it anyway. Okay, but we refer to this by T pulse width, or we have the pulse width here. We have a constant. This is depends on R and C. We have some sort of a relationship between timing and RC constant, or the multiplication of R and C. That means the timing component, okay, the resistance's value times the capacitance's value, and we have the proportionality constant K, You will not have to determine it. We will give it to you soon enough based on some applications. Now, for RC is constant for a fixed circuit. That means if we have a circuit that has R and C, it won't change. This will remain constant. As long as you don't change R and C, they remain the same. And for that circuit, for the monostable, we are speaking about it, as we said earlier, for the TPW, or the duration of the pulse width, for the instability period, or in that case like this, when we trigger it, we have this kind of equation. TPW, or pulse width, is equal to K times RC. This is the proportionality constant. You see we have proportionality here. When RC, this multiplication, or this component, these two, if they go high, the pulse width goes high, and so on. How do we determine T? You don't determine it. We will give it to you ready based on the circuit, the given circuit. Now, this is one of the compositions, or actually the configuration of a one-shot monostable logic timer. And what we have here is an external resistor and external capacitor. Why? Because we may have also internal resistor and capacitor, but for the time being, this is exactly how we link it, or how we configure it, how we connect them. We have a trigger here. What is this circuit? We will explain about it in a while. You just need to know, like, we have Q and Q bar is very similar to a flip-flop. It's not exactly a flip-flop, but it's very similar in this case, and we have the high voltage connected through R and C. We have a charging path, and then we must have also a discharging path, and we will see how. Now the idea is like this. We may have two types from the one shot. One shot again is monostable. Monostable, that means it remains in stable state unless you trigger it. So if when you trigger it, it starts going to its unstable state, and in its unstable state the counting starts. So we will create a pulse like this, okay, based on RC with, of course, proportionality constant. All right. So we have, based on that, we have two types. One of them we call it non-retriggerable. That means while it is in its unstable state, if you trigger it, nothing will happen. So let's say it is in its stable state, you trigger it, it goes to unstable state and keeps on moving until it goes back to its stable state. While it is in its unstable state, if you trigger it, nothing will happen. It will just ignore that triggering. But for the retriggerable, if you trigger it while it is in its unstable state, it will expand, or actually extend, the time period of its instability time. That's the difference between non-retriggerable and retriggerable. Retriggerable means what? You can expand its time by retriggering it, and that affects the whole process. For the non-retriggerable, if you retrigger it during its unstable time, it won't do anything, it won't change anything. So all this explanation is about it. So if we have extra, now look, this is, let's say, a trigger. A trigger, by the way, before I go further, a trigger we refer to a pulse similar to the clock, usually. Okay, so that's the trigger. It may be only once, it may be repeated. It depends on our application, okay? So now look, if we have a trigger like this, and this is periodic, as you see, it repeats itself based on certain period. Now we have again a repetition of this pulse, and so on. Now look, the output will be like this. Once it is triggered, it will start its unstable period until TP is finished. It will go back to its stable period, or sorry, stable state, not period, stable state, until we trigger it again. If we trigger it again, it will go back high. Now here's the thing. This triggering is next to its unstable state. This is the unstable state, okay? Here is the unstable state. Now, once it goes back to low, that means it's stable. Here is the stable state, here is the stable state. Now look, we are triggering it again when it is stable. that means it will just create a new pulse again. Okay, a new pulse here again. Once it is done, we are receiving also again the stability, then retriggering again. No problem for this case. But if it is non-retriggerable and you try to retrigger it during its own unstable time, this one will be ignored. Nothing will happen. So as long as it is not in its stable, this is stable, in its stable state, the trigger will be ignored, like this, will be ignored. This may be an exam question. I may ask you about these. What will be the reaction of this kind of non-retriggerable monostable timers? Okay, these will be ignored if it is non-retriggerable, as the name indicates, that you can't retrigger it while it is in its unstable time or unstable period, because it's already triggered. So retriggering it will do nothing. You will have to wait until it goes to the stable time. If you retrigger it, nothing will happen. It will just do nothing, and things will go on. For the retriggerable, now, as I explained like a few minutes ago, if you retrigger it during its unstable time, like here now, it will expand it, it will extend it. Now, how? I will explain it to you. Now, look at the trigger. Now, let's say we have this instability period like this. For the instability period, if it is just TPW like here, we are not triggering during its instability period. This is stable, so we are triggering it again during its stable time or stable period, stable duration. So we get again instability with no problem. But look, if we trigger it and we get our unstable started, or we have our stable started, what will happen? Simply, if we retrigger it again, we will start the process from zero. It will start having PW, or the beginning of the instability duration, from here, not here. The time you retrigger it, it will start having to count the whole TPW again. If you retrigger here again, it will start from here again, and so on. Okay, this is the important part. So this is the difference between these two. The non-retriggerable, nothing will happen, it will not be expanded. This one will be expanded. You will start recounting the duration of instability from the beginning of the next retriggering, even during the instability time. Okay. Now we have certain types of timers. There are so many of them. We are not going to teach them to you. We will just give some examples of common timers, so that maybe one day if you are going to design an electronic device or something, if you require it in an IC, you will know what it is. We have the 7421. This is non-retriggerable. Okay, and we have the retriggerable 47XX122. Okay, so we will study these two types. One of them non-retriggerable, and one is retriggerable. So this one, it will not be affected as long as it is still in its own instability time. And if you retrigger it, nothing will happen. Now look, we said earlier about the equation. We have the TPW, the time for the instability, which determines the pulse width in this case. We have 0.7 RC external. Now for R, it could be an internal resistor. As I said earlier, it could be an internal R, and if it is internal R inside the chip, on chip, that means it would be 2 kilo ohm. If it is not, it will be determined by the question. So let's say if we ask you a question like this, let's say we give you what is the pulse width of 7422 timer, one-shot timer, and this timer, the C external or the external resistor is given by, let's say, 0.1 microfarad, for example, and R is an internal resistor. If we say that, then R is 2 kilo ohm. I don't have to give it to you. You don't assume it. It's already given by 2 kilo ohm. So you multiply these two, multiply it by 7, the proportionality constant in this case is given, and you will get the duration. the pulse duration or the pulse width in this case. Okay. We have for the retriggerable, we have another equation. Usually I get these questions like, from where did you get this equation? Of course, it has a derivation. You don't have to worry about it. Don't worry about this derivation. You don't have to care about it. Okay, you just need to remember those, and it's actually not hard. This is 0.7 RC external, then this is 0.32 RC external. Now remember, this is 74XX122. This is retriggerable. Retriggerable, okay? And here we have, if the internal resistor not 2 kilo ohm, it's 10 kilo ohm. So if I don't give it to you in a question, it's 10 kilo ohm, consider it 10 kilo ohm. If I give it to you, that means it's external, it's connected externally and use its own value, okay? So the proportionality constant here, K, is equal to 0.32 RC external multiplied by 1 plus, not C, I'm sorry, 0.32 multiplied by 1 plus 0.7 over R. This is the proportionality constant. You don't have to worry how they derived it. You just need to use this equation if you are asked any question during the exam about it. Okay, we have a very important type of timers, the 555 timer. 555 can be an oscillator, it can be a one-shot timer, it can be, as I said, monostable, it can be astable. That means one-shot monostable multivibrator, or it can be pulse oscillator. Pulse oscillator is a multivibrator, but it's astable. That means it has no stable state. For this one, monostable, it has a stable state. It goes unstable when we start triggering or when we trigger it, and then it goes back to a stable state. Here, astable, it doesn't have any. For the astable, it doesn't have any stable state. It keeps bouncing, okay? Something like that, between two states. How do we have these two? We have the same chip, 555. It's a chip. If we connect R and C based on certain configuration, we will get either monostable one-shot or a pulse oscillator or astable. So it depends on the configuration of R and C. Now R and C, now look, this is 555. These are the pins. Do you need to memorize them? No. I would never ask you such a question. Memorizing these pins, what they are. I would bring you a question like this to calculate maybe the duration, to calculate the frequency, maybe to explain how it works. Yes, that's possible. But I don't want you to memorize things with no understanding. You don't have to do that. Now look, the most important thing is that now the connectivity, R1 and C1. Now these two are extremely important. Look at the output here. And this is for just decoupling. Now C2, you don't have to worry about it at all. It's usually a very small capacitor, and this capacitor, like you see, is small, and in that case it's just used for lowering the noise at the output. Decoupling, that means it just isolates something from another. That's what it means, decoupling. And it's optional. We can drop it out even if you find it like connected to ground directly with no capacitor, you don't have to worry. We have the connection of ground. We have an internal transistor. That transistor is extremely important. It determines the operational process of this timer. Now we have the reset, we have the discharge of what? C1, no, not C2, ignore C2 while discussing this. C1. Now C1 will charge by VCC through R1, and we have a trigger here. So initially what will happen, we said earlier that this kind of monostable usually goes like in one stable state, then we trigger it, it goes to unstable state, it keeps counting, then goes back when its pulse width is finished to its stable state. That's exactly how it happens. Now we have this constant of proportionality, 1.1. Please do not ask me from where you got it. It has a way to derive it. You don't have to worry about that way. But R1, C1, this is the pulse width. Very similar to this here. But this is another design. It's not the 74121. Rather, it is 555, one shot or monostable. Okay, 1.1 R1C1. Now what happens? Initially, now assume that initially the output is low. Assume, just an assumption. What will happen? Now, before anything goes on or before anything starts, we have an internal transistor. Internal transistor, how it is connected, you don't have to worry about it. But as long as the output is low, the transistor is on. This is important, please pay attention to it. And if it is on, that means it creates a path for this capacitor to discharge. Imagine like it is a switch connecting this capacitor to the ground. If you connect this capacitor to the ground, it will be discharged. It will not keep any charge. So as long as this one has an output 0 and the internal switch or transistor in this case is on, then what we will have this one discharged. If we trigger here, if we apply a trigger to pin 2, what will happen? In other words, we are giving an instruction to the internal transistor to go off. If it goes off, this capacitor has no way to discharge, and the path from VCC, the supply voltage, through R1 to C1 will start going. We will not have a path to go to the ground. We will start charging. And in that case, C1 will start charging and the 555 will go to its unstable state. C1 will keep on charging until it will reach to 1/3 of the VCC. Why 1/3? This is the design, okay? This is the design of the 555 in this case. If you want to go deeper, how it goes based on some mathematical equations, you can Google it, you can search about it, but it's not really necessary for your, level and type of study. You just need to remember that we go up to until 1/3 of VCC. Once we go to that level, what will happen? The output will go back low, and that means the internal resistor will kick in. That means it will go on. And once it goes on, again, this switch creates a path here to this capacitor to discharge. And what will happen? We will go back again to our stable state. So initially stable, the capacitor C1 is not charged. When we trigger, it starts charging and the output will be high until, I'm sorry, this is like one straight line, okay? Until TPW, T pulse width, or the time of the pulse width is finished, until we reach to 1/3 of VCC in the charge of C1, then it will go back again low to its own stable state. Once output will go low. If we don't trigger it, that will be the end of this. If we re-trigger it based on certain period, we will have this one repeated over and over again. Okay. This is the exactly the idea of 555. Again, to explain about it so that you don't get confused, let me remove whatever I type so that you can see it clearly. Let me repeat the whole process, or repeat what I just said, so that if you couldn't understand from the first time, now you understand. Initially, we have the output low, okay? Now we have, this is the supply voltage. Any chip needs a supply voltage, okay? And we have a trigger, and this trigger will control the process of the internal 555. We have some switch, or you can call it transistor. In this case, transistor works as a switch. That means on and off, okay? Connect or disconnect, it depends, okay? Now, what we need to do is pay attention to VCC, its connection to R1 and C1. So C1 charges through R1, this charges through 7, okay? That's the way. Now, what we have here is an internal transistor which is on as long as the output is low. If we trigger the internal, this chip, what will happen? The output will go high, and this transistor, internal and transistor, will go off. So off means what? It is like, initially I was connecting this part, C1, to one here. Like in this case here, just directly, okay, to 1, means I'm connecting C1 to 0. Ground means 0. That means it will not keep any charge. But if I open that connection, if I say this connection we have here, open it. Okay, this is just in basic sense. Open this connection, disconnected. What will happen? We have a path from VCC to C1. As you know, you studied this in electric circuits or in physics actually. The current follows the easiest path, like us human beings. We follow the easiest path. The electric current goes to the easiest path. If we have a ground here, we will go to it, we will not go to the CC. If we have this CC in parallel with the ground, it won't go to C. We won't go to C or C1 here, we will go to the ground directly. But if this one is open, okay, if this one is open, in that case what will happen? We will just have the following. We will have a charge, a path for the charge through R1 to charge C1. C1 will keep on charging until we reach to a certain threshold. This threshold is 1/3 of VCC. Once we reach to that level, output will be low and the internal transistor will connect back again C1 to the ground, and it will discharge in that case until it will reach to its 0 state, I mean as a charge. If we trigger again, then we will restart the process depending on the trigger. If it is a clock, if it is just one pulse and then that's it, it depends. Because we may need to only create a timer for one time, or we may need to create a timer for multiple repeated applications. Now, one-time timer, there are a lot of applications in one-time timer. Think about something like the microwave, something like your own maybe, I'm not quite sure, but if you set up a timer for certain things that you need to achieve them only once, there are a lot, like maybe a washing machine or whatever you set your time, that's only one time set timer, then it is done. If you want it to be repeated, then you have to create this kind of triggering based on certain periods so that your timer goes on back again until it finishes, you trigger it again, and so on. Okay, this is the one-shot 555. Okay, let's take a simple example. This is just an application example, and this is as hard as it gets. You will never get a harder question like worse than this in the exam. This is not my target usually, because we are teaching you as a software engineering students this kind of course, not exactly as those who study electronic or any other relevant department. Usually they take this one in more details, but for your case, no. We are just giving you an idea so that you know how to design if you are required to design such a thing in the future. Okay, what is the output pulse width? Now, output pulse width, TPW, okay, for a 555 monostable circuit. Monostable means one shot, means this one we just said about it. Okay, with R1 equals 2.2 kilo ohm and C1 is 0.01 microfarad. Now remember that we have an equation says 1.1 times R1 times C1. This is TPW, okay, the time of the pulse width. And you just need to multiply that, nothing else. Nothing else. And remember one thing, because also during your exam I found a lot of you fall in this mistake, so you guys should pay attention. Do not fall in this mistake. I would say most of you really fell in this mistake before during the exam. This is a kilo ohm, this is microfarad. Now pay attention to units. Okay, multiplied here by 10 to power 3, here multiplied to 10 to minus 10 to minus power 6, or here 10 to minus 6. That's how you should be careful about these. Okay, if you multiply here, so here we have 10 to power 3, here we have 10 to minus 6. See the outcome, how it will be and by which unit. Okay, you want to put it in milli, you want to put it in micro, it's up to you, but just keep your standard. All right. Let's take the other example, the 555 timer as a stable, as an oscillator. Stable means what? A stable here goes from one state to another, never has a stable state. It's always unstable. It keeps on oscillating or bouncing. Okay, so we don't have exactly any external trigger. Now look at this. We had an external trigger here. For configuring the 555 oscillator in this case, we don't need a trigger. It's unstable by itself. It keeps on going, bouncing between two levels, and this is what we refer to by oscillating, or we refer to the device by oscillator. Oscillator means a device that keeps bouncing, something like this, okay? And that's how it's created. Usually it's not exactly like this. We have something like this. We have something charging, discharging, charging, discharging, charging, charging, discharging. And if you connect these dots like this, you will have high, low, and something like that, okay? Like some type of, maybe something like this. Let me delete this one. Let me remove this one. I'll redraw it. Okay, something like this. Let me draw it properly here. We have something like this, charging, then discharging, then charging, then discharging, then charging, then discharging. So we have like the time high like this. Up until here. Then the time low and the time high. Let me remove this one. Again, the time low, then the time high, low, and so on. So we create something like a pulse, like the clock, based on charging, discharging, charging, discharging of this process. All right. Do you need to know this one? You don't have to. I'm just explaining to you about the concept, how it keeps on bouncing between two different levels, based on charging, discharging, charging, discharging, charging, discharging. Okay. Now look at the configuration. The configuration now, we don't have only one R, VCC, R1, C1. No. We have VCC, R1, R2, C. We don't have any trigger. Remember, we had trigger before, right? Now trigger is connected internally, connected from the circuit itself. We don't have an external trigger. The circuit itself will trigger this 555 as a chip. So what happens? It's exactly like this. Now initially we have the output as low, and again our transistor is this one is a bit different. Now what we have initially, if the output actually is low, what we have is, now think about this. Now let me show you the connection. Now we have C1 connected to trigger. Initially, if C1 is not charged, because if we start the beginning of, because it has to be either charged or not charged, okay? If it is not charged, there is no trigger, it's 0, and in that case what we need to do is we have some internal transistor acting as off or open, okay? And in that case, if the transistor is open, we have our path here ready for charging. Why? If we have a path here connecting the ground through a transistor, this one will never charge, okay? It won't charge. It will just go to the ground. So we have this kind of path now through R1 and R2. We will have C1 charging. It will charge through R1 and R2 and will reach to 2/3 of VCC. How? Do not worry about it. How? It has its own equation and its own derivation. But what you need to know is, you need to remember, it will charge up to a level. This level is 2/3 of VCC. Until then, the internal transistor will become high. How? Because of this kind of configuration. When this one reaches to a certain level, this will be triggering the internal transistor to kick as on, and then it will connect to the ground. We will start discharging, not charging. Why? VCC will have a shortcut to the ground, and also C1 will have also direction to the ground, will start discharging. It will discharge not fully until 1/3. 1/3, what will happen? Again, the transistor will kick off and we will start recharging again. So charge to 2/3 VCC, discharge to 1/3 VCC, charge, discharge, charge, charge, discharge, and so on, bouncing between states, and that will create exactly the output waveform. And usually this output waveform, as I said, it's a square pulse. It's like the exact clock that we usually use in many applications. Okay. Now for R1 and R2, along with C1, are the exactly timing circuit. Do you remember this timing? Sorry, here. Timing section. They determine the time. Why? Because we said we will go to 2/3 VCC, 1/3 VCC, but based on what time? What's the duration for charging, discharging, or the bouncing, in other words? Okay, that's exactly determined by what, as I said, it's determined by, this is the whole frequency, Now this one, as I said earlier, R1, R2, RC, will determine the oscillation, the period. Now, as I said earlier, for this one, you can even ignore it. It's just decoupling. You don't have to worry about it totally. There is no much of a worry about it. Okay, now look at the frequency. How did we obtain this kind of equation? You don't have to worry about its derivation. Just use it. The frequency of the output here, because it's an oscillator, this oscillator is determined by its frequency, or the period of its oscillation. The period is the reciprocal of frequency, or the frequency is the reciprocal of the period. So it depends which one you are going to get. 1.44 divided by R1 plus 2R2 times C1. This is the way. Try to memorize this formula. Nothing else will be, requested from you. We have a graphical representation to calculate this one. Usually we don't ask questions about this. It can be graphically. You can obtain the values here graphically of the frequency based on C1, and then the intersection with R1 and R2. It needs a very specific type of printout to determine based on like a precise, levels here or numbers. It doesn't matter for us. We can calculate it mathematically here. Okay. Now for the time we said charge, discharge. We have time high, time low. Okay, because this is based on oscillation. Time high is the time the 555 takes to charge, goes from 1.3 to 2.3 VCC. This is what we refer to by time high. Now remember, let me explain to you so that you don't forget it. Now C1 charges through R1 and R2. Of course, it charges by VCC. So remember this. So it is T high will be 0.7 times R1 plus R2 C1. How did I get 7.7? Don't worry about it. It's derived. It's given to you as ready. Now why R1, R2? Because it's charging. C1 is charging through R1 and R2. Now look at the T low. It's the time it goes from 2/3 VCC to 1/3 VCC, or 2/3 VCC to 1/3 VCC. That's the discharging time. Discharging, C1 discharges only through R2. Look here. This is the path, discharge. So R1 has nothing to do with it. Now look. T low equals 0.7 R2. R1 is gone. C1. Okay? So that's how you memorize and make the difference between these two. Now we have the time high, time low. Remember before in the first chapter, I think, or the second chapter, time high plus time low composes the whole period of the signal or the oscillation. Because we have time high, time low, time high, time low again, repeatedly. That means we have the period. So if you add these two together, you will get the whole period. Okay, 0.7 R1 plus 2 R2 C1. If you take its reciprocal, that means 1 over T, that's the frequency here. 1 over 0.7, that's 1.44. Okay, and then this one would remain in the denominator. Okay, so if you have the time, you can get the frequency. If you get the frequency, you can have the time. But if you are requested to get time high, you have the equation. If you are requested to get time low, you have the equation. Okay, and we have one important thing, the duty cycle. I asked this one also during the exam for another signal, but it's very important. The duty cycle is defined by the time high, the percentage of the time high to the whole period. That means we will look for the time high over the whole period multiplied by 100, so that it will be 100 as a percent. So time high over time high plus time low. Why? The whole period is time high plus time low. Now remember that the time high is this, 0.7 R1 plus R2 C1. Now this is the time low. You can rearrange this in this form, R1 plus R2 over R1 plus 2 R2 times 100, it will be as a percent. We may ask a question from this. This is just a direct application. Let's take just a simple example to conclude the whole chapter. 555 timer configured to run in a stable mode. Now remember, a stable means pulse oscillator keeps oscillating. It's unstable. Okay, it's shown below. Now remember that we have R1, R2, okay, and C1. All right. Determine the frequency of the output. Now remember, the frequency is given by the equation 1.44 divided by here R1 plus 2R2 multiplied by C1. Try to memorize it. Practice, try to memorize it. Okay, I'll give you some questions to do that. If you get the frequency, now determine the frequency of the output and the duty cycle. So we have everything we need, so we just need to apply 1.44 divided by R1 plus 2R2 times C1. Now only mathematics here, just you need to, properly divide, add and multiply and so on. For the duty cycle we said earlier, is given by this equation, R1 plus R2 over R1 plus 2R2 multiplied by 100 to get the percent, and in that case you will get the percentage. It doesn't matter. If it is less than 50%, more than 50%, it doesn't matter. Even if it is too little, it depends on the time, charge and discharge, okay? So that is how we solve these questions. That is how difficult it gets. It will never be harder than this. It will be direct application if I ask you any question based on this. If I ask you to explain how the 555 let's say a stable timer is running, you can explain to me this way. Like you can say initially C1 is not charged and the switch is on if we have a certain like a level of charge more than 1/3, let's say, goes, then here we will have like an off state, and this off state will get us C to start charging until 2/3 of VCC, and when it charges to 2/3 VCC, the internal transistor will kick on again, and then once it kicks on, we will start discharging until 1/3 VCC again, and so on. It's all written here, but as I said, if you feel that it is really complicated for you to understand it, this is the way I explained it, and that's enough. Initially, as I said, we have C1 uncharged, then we will have like some internal transistor off, we'll start charging, then it will take a certain level of charge to 2/3. When this one will kick on, then discharging through this kind of pin, and so on. Okay, actually that's it, and this is the end of chapter 6. Tomorrow we will have a live session. Yes, for 22nd of December. Yes, we are going to have a live session. We will have a new chapter. Okay, I will also discuss with you some extended tutorial. Until then, have a good time. Goodbye.